In EICASLAB, you can implement your control algorithm by following your own control design methodology. In particular, you can follow a model-based approach, and you can distinguish between the model used for designing your control, here called a simplified model, and the model used to simulate the plane to be controlled, here called fine model. The simplified model is typically linear and time invariant, while the fine model is typically non-linear and time variant, and includes all the aspects neglected in the simplified model, but that may act on the frequency band of the control and may affect your control, such as hysteresis and backslash. This approach, called the two-model approach, allows you to test and tune your control algorithm by assessing the limits of validity of the simplified model. Of course, the choice of the simplified and fine model represents a crucial point. A control based on a not appropriate simplified model cannot run correctly, and if your fine model is not accurate enough, it will not be sufficiently representative of reality, and consequently you can obtain good results in simulation, but then on field the control could work differently. On the other side, a fine model too accurate may lead to useless and long computation and simulation time without providing significant results, but with the risk to introduce errors or noise. Another outstanding characteristic is the fact that oriented libraries implementing specific key functions are at your disposal for supporting your control design, and that powerful algorithms are available for carrying out your system simulations. For supporting you during the system design, each working area is equipped with libraries oriented to specific application sectors, such as robotics, automotive, space and economics. Predefined models for engines, robots and others are available, depending just on a set of parameters. Besides, we offer, for specific sectors, libraries allowing not only an automatic generation of code, but also a control algorithm generation. The libraries are also easily customizable by the user, who can complete them according to its need. To integrate in simulation the system of differential equations used to represent a continuous plane to be controlled, a fully original proprietary integration procedure is available, specifically developed for overcoming the frequent difficulties met as a consequence of the numerical errors. The procedure requires a resolution value for each state variable, strictly linked to their physical meaning. To perform the model parameter identification of the planned simplified model, an original identification method is available in EICASLAB, oriented to estimate the best values of the planned simplified model parameters from the point of view of the control design. To perform control parameter optimization, a powerful numerical optimization algorithm is available, which allows in very reasonable computing time to get the optimum value of a large number of parameters. As already anticipated, in simulation, a like real-time technique is applied capable of faithfully emulate the execution of the control architecture running on the final target. All the activities assigned to the planned mission and control areas, together with data transmissions among blocks, are executed by strictly following the scheduling constraints set out by the user in order to reproduce the order in which these activities will be really executed in the final target. Starting from the modeling and like real-time simulation operative mode, the application software that represents the target-independent part of the final code to be transferred in the final target can be automatically generated thanks to the EICASLAB LCG module. We point out that the application software, generated and preliminary tested in like real-time in the modeling and like real-time simulation operative mode, will be exactly the same application software that will be transferred in the final target. In particular, Moving to the Rapid Control Prototyping operative mode, you keep the very same application software, and it will be linked to a specific basic software, here indicated Basic Software RCP, generated for managing the real-time scheduling and the processor interfaces. Moving to the target operative mode, the application software will be transferred to the target without any modification, and it will be linked to a specific basic software, here indicated Basic Software Target, generated for managing the real-time scheduling and the target interfaces. In modeling and like real-time simulation operative mode, you have at disposal a set of tools that help you design the overall control strategy and perform a preliminary test of its performance in a powerful simulated environment. First, the master tool allows to manage the EICASLAB projects and runs, for each operative mode, suitable and powerful software tools necessary to develop, test and validate the overall control algorithm. The Sim Builder tool allows you to implement your plant model, your control strategy, and to configure the simulation environment. The Sim tool allows you to perform like real-time simulations, which represents the first level of test of your control strategy. You can then post-process any data obtained during the simulation using the Post tool. And through the MPI CPO Manager tool, you can perform model parameter identification, specifically devoted to identify the parameters of the plant model, and control parameter optimization, specifically devoted to optimize the control algorithm parameters. In the following movie, the modeling and like real-time simulation mode implemented for the Amazing Ball will be illustrated.